Okay, let's start. Good evening, everyone. So today is problem solving session 12. And as this is the last session of this course, so I hope till now everything is, going good. And I hope this session will also go good. So yes, good evening. I am Sakshi Bhardwaj and I'm a TA of Professor Sudarshana in Chemical Engineering Department, IIT Roorkee. And I'm a PhD scholar under Professor Pradeep Kumar Maji in Department of Polymer and Process Engineering, IIT Roorkee. And yeah, this is the course Polymer Process Engineering and NPTEL Problem Solving Session 12, in which we are going to take assignment 12 related questions. So let's start with a brief introduction of mine. So I am in the Department of Polymer and Process Engineering, Indian Institute of Technology, Roorkee, under the care of Professor Pradeep Kumar Maji. The topic of my research is fabrication of cellulose-based aerogels for thermal management applications. Apart from this, I've done my master's from Maharishi Dayanand University, my bachelor's from Tirodimal College University of Delhi. Apart from this, I've conducted two research projects, one in Indian Institute of Technology, Roorkee, over lightweight thermal superinsulating aerogels, and another one in University of Delhi, over repurposing of drugs and validation of lead compounds. So moving on to the last session. So here, as till now, we have read different type of polymers, their properties, their formation techniques, their different phenomena like heat transfer, mass transfer, the processing, how they can process, and in which areas it can be applied. So this is the last in which we are taking different polymers for applications like sports, medicines, and others. And this is a mix of all the sessions. It's not exactly based on one topic. So we are going to take many multiple topics in this based on maximum applications. So starting with this, yeah. So polymers are versatile materials used in diverse fields due to their lightweight strength and flexibility and durability. Because they have multiple properties like lightweight, they are their strength, their flexibility, and durability. And that's why in sports, they replace metals or wood to make equipment light and stronger. For suppose it's rackets, bicycles, golf clubs, and all these things. They are now made up of polymers. In medicines also, some biocompatible polymer like gutta-percha and polyurethane are critical for dental fillings, implants, adhesives, and coatings for such things like this. And they should be biocompatible if we are using in medicine, because if you're using in anybody's body, it should be biocompatible. And then if you look at the growing trend to some sustainable and bio-based fibers like natural composites to reduce dependency on petroleum-based plastics. So here, because of this petroleum-based plastic and their non-biodegradability, some sustainable and bio-based fibers or natural composites, such things are uh, using these days. And if you look at different, the applications like in the cooking stuff, Teflon is a polymer, rubber is a kind of a polymer, plastic is a polymer, the clothes we are wearing is a polymer, sugarcane contains a polymer, DNA, RNAs consist of a polymer, wool consists of a polymer. So everything, if you look around, we are, surrounded by many polymers. Some are uh, the synthetic ones, some are the natural ones, some are the bio-based, and so there are different polymers we are surrounded by. And that's how they can be used in different applications like sports medicines and etc. So based on this, we are going to take some questions and going to cover some topics overall. So yeah, if you look at the specialty polymers in dentistry and industry. So if we look at the dentistry and industry, so there's a polymer named as gutta percha, which is a natural polymer used in a root canal fillings. And because it's biocompatible, inert, easy to shape, and that's why if you look at the structure, so this is the isoprene unit. If anybody of you have read about the rubber technology, so this is a basic unit rubber technology in rubber. consist of. And if we look at this, because of these repeating units, it behave like a rubber. And if you are going to form these structures in like cis and in trans form. So cis is like in which the groups are on the same direction. Trans is like the groups are on different direction. This one and then this one. So if it's on the different direction, it's known as the trans 1,4 polyisoprene and it is named at glutapurt. And this can be used in dentistry and industries. If we look at the other polymer, which is serine, or it's ionomer resin, so because of its transparency, impact resistance, widely used in packaging films and sports equipment like golf balls and all these things. That was the structure of this serine polymer. Polyurethane, we all know and we have read about in the last sessions also about the polyurethane because they can find in the adhesives, coatings, foams, and medical devices. They can be used. And there is a cyanoacrylates. So in the last session, we have read about the acrylates in which acrylic acids and they can be used as adhesives or super glues for instant bondings and in sports gear and even medical wound closure. So these kind of polymers we can use in medicines and dentistry and different industries. So this is the structure of cyanoacrylates. You can look at this because of the cyano. This is cyanoacrylate. So moving forward to the questions. So the first question is, what property of gutta-percha makes it ideal for use in root canal treatments? We just read that gutta-percha can be used in root canal treatments. So now they are asking about what property of it make it useful for root canal treatments. The options are A, its biocompatibility and flexibility, B, its ability to bond to enamel, C, its taste, or D, its whitening effect. So what else among them can be used? Got two answers. It says it's A, it's biocompatibility and flexibility. So let's see the answer. Yeah, it's A, it's biocompatibility and flexibility. So gutta percha is natural rubber-like material commonly used to fill the cleaned and shaped root canals. After endodontic or root canal treatment, its ideal properties for this purposes are first because of biocompatibility and another one is flexibility. Biocompatibility means that it is not harmful or toxic to living tissues. Because we are using it in the body, so it should be like compatible to those. Since it's come into the direct contact with the internal structure of tooth and surrounding tissues, it should cause inflammation or adverse reactions. Another one is like flexibility. So this can be softened when with heat or solvents, allowing it to adapt or to mold to integrate shape of the root canal system This helps ensure a tight seal, which is crucial to prevent reinfection. So because of its flexibility, it can be reshaped or remolded into this, and that's why it can adjust according to your, the root canal system, and which is like, it should be compatible, kind of. So biocompatible and flexibility are two main important properties of this root aperture, which makes it, perfect material for use in root canal systems or treatments. Okay, then moving to the next question. Serine is a primary composed of which copolymer? So we just read about the serine, like it can be used in a sports equipment and as a polymer. Uh, why it can be, what it is composed of, which copolymer? So there's options like polystyrene, cobutadiene, polyethylene, comethacrylic acid, polyvinyl chloride, or polylactic acid. So which copolymer it is composed of? Okay, so I got two answers, which is it's B, polyethylene co-methacrylic acid, and yes, the answer is B. And the reason is, if you look at the structure, so it is a heating unit because this is the ethylene unit and this is a methacrylate unit. So this is a copolymer of ethylene and methacrylate unit. And if you look at this, so lean is a thermoplastic monomer resin developed by DuPont. It is made by copolymerizing ethylene with methacrylic acid. After polymerization, the methacrylic acid groups are partially neutralized with alkali metals like sodium or potassium or zinc ions, creating ionic. If you look at the position, so these are the ions creating ion crosslinks. The structure gives Solene its unique combination of toughness, flexibility, transparency, and resistance to abrasion and impact. And that's why it can be used in sports, because in sports, if you are using an equipment or something like this, you will use it again and again and again. So the material should be, tough, flexible, and it is abrasion and impact. It should be abrasion and impact resistant to use in that. And cost wise, if you look at it, it should be cheap because you cannot, purchase that costly sports equipment every time. So every factor look into taken into the account, and then we can form some materials like this. So Sulene is a copolymer of polyethylene co-methacrylic acid. Okay, I guess this is clear. Then moving forward to the Next question. So, which of the following is not a common application of Solin? Golf ball covers, insulation for electric motors, cosmetic packaging, and blister packs. Which of the following is not a common application of Solin? I got answer. B, yeah, it's insulation for electric motors. So Silene is because it's ionomer resin, which consists of copolymer of ethylene and methacrylic acid, developed by DuPont. It exhibits these properties. There's these. So they can be applications in packaging films, blister package, cosmetic containers, golf balls, covers, and some sports equipments. uh, Ionomeric nature gives toughness and flexibility, but yeah, because it cannot be used as insulation for electric motor. So this is a different application. Otherwise, golf ball covers, cosmetic, and blister packs, Solin can be used because of its properties like these. Okay, it's simplification based on just application. So moving forward. Okay, so we just read it in the last session also because we have some questions over it. I've just added a slide again and we're just going through it in a just quick way. So natural fiber reinforced composite materials. It's a very important term nowadays because natural fibers can be used in for reinforcement composites and natural fibers such as jute, hemp, flax, silk, coir, or cotton. So they can be used to improve the mechanical properties of final product, and because of their lightweight, biodegradability, their mechanical strength and toughness, their renewability, thermal insulation, and low cost, can be used in many applications like automotive components, construction materials, sports equipment, furniture, packaging material, and consumer goods. So these kind of application can be targeted with natural fiber reinforced composite materials, and such a materials can also be used in sports and everything like this. Have a little bit written it here. If we look at the question, so which property of natural fiber composite makes them attractive for sports application? So this is particular asking for sports applications. So which fiber of natural fiber composite make them attractive for sports applications? High density, low renewability, poor mechanical strength, low cost, and biodegradability. It's a very simple question. You can just predict the answer by looking at it. Okay, so I got two answers. And this is a simple question of because of low cost and biodegradability, natural fiber composites can be used in sports applications and other properties like it has low density. So it do not have high density. It do not have low renewability. It has high renewability, and because of their poor mechanical strength, it's also because they have high mechanical strength. So these kind of properties make them useful in sports equipment such as tennis racket frames, bicycle frames, surfboards, canoes, and protective gear. So these natural fiber composites can be used in application areas like this in the sports particularly. Okay, then moving to the next question of this. Yeah, so polyurethane are formed by the reaction of, because we have taken polyurethane in previous slides and in previous sessions, so we have an idea about like what polyurethane are consist of. So are they made of epoxides and amines, diisocyanate, diols, olefins and dienes, and hydrates and diamines? Yeah, I got two answers, which says it's P. Polyurethane are formed by the reaction of diisocyanate and diols. So yes, it's P. And if you are looking at the structure of polyurethane, so they form with this carbamate and urethane linkage, and generally diisocyanate with diols. And if you look at it, this is the isocyanate group, and the are diols or polyols, kind of, we can say. And if you look at the structure of polymers, so polyurethane form by the rearranging of these groups. And if it rearrange it so to form like a linkage of this, where you can see this H rearrange according to this NH and then C double bond OO. So this kind of linkage we know generally known as urethane linkage. It's formed in polyurethane. And as we have already read about the properties because of this many exciting properties like flexibility, low weight, and other things, it can be used in electric system. Because first we read about polyurethane as electric coating. So on electric parts, it can be used as a coating over it because of its insulation properties. And apart from this, it is also used in medical medicines and sports industries because of its exciting properties. So polyurethane is a very exciting material, and it has a multiple use everywhere. Okay, so I hope this is clear because it's related to the last sessions itself. So moving forward to the next question or a topic. Okay, so this is a fiber spinning and properties. The topic name is fiber spinning, and the fiber spinning is process of converting polymers into fibers. And we can use different techniques like melt, wet, dry, extrusion spinning to change polymers into fibers. So the extrusion spinning common for synthetic fibers like polyester, nylon, and polypropylene. Key properties of fibers, there is tenacity, which is like strength per unit thickness. Elongation at break, ability to stretch before failure. At that point where we can stretch the polymer to form a fiber before its break. Controlled by drawing and heat setting during fiber production. So it is generally controlled by drawing and heat setting. And specialty fiber like veteran and have high tensile strength and modulus make them ideal for sports and aerospace applications. So if you look at this, the setup for the fiber spinning, in which it's a polymer solution, then it is filtered and then it goes through the spin bath where it is drawn into fibers. It passed through the spinnerate. Spinnerate have these openings where this polymer solutions is passed through, and it can contains like fiber like this. And then due to this, the two mill roll, the fibers are collected into one, and then it can be stretched and drawn like this. And then in the wash tank, it is washed, rolled, applied fiber finish, then drying, and and lastly cutting or take a package, whatever you require. So these kind of process in which polymers draws into the fiber is known as fiber spinning, and then they can be used for multiple properties. Like if you look at the badminton racket, so the fibers like structures to form the main structure of racket. It is also from the polymer. So how the fibers are formed? So these structures, these techniques. By these techniques, that fibers can be formed. So based on this fiber spinning and properties, let us take some questions. And the first question is, which fiber spinning process involves dissolving a polymer in solvent and extruding into coagulation? So they are asking like there are many fiber spinning process, melt, wet, dry, electrospinning, and which fiber spinning process particularly involves dissolving a polymer in solvent and extrude into a coagulation bath. I am expecting some answers. Sorry. Okay, I just got a single answer, although I'm expecting many more. Okay, then let's move forward. So the correct answer is B, yeah, wet spinning. In wet spinning, the polymer is first dissolved in a suitable solvent to make a viscous solution, and then the solution is extruded through a spinnerate. plate with a tiny holes, like we have seen in the last section, the last slide, the spinneret. Yeah, spinneret, a plate with tiny holes directly into the coagulation bath containing a non-solvent. So here this is a non-solvent. Suppose polymer is getting dissolved in some organic solvent, so we are going to take some polar solvents in that. So it's a non-solvent which cannot dissolve the polymers, and the non-solvent cause the polymer to precipitate out or to coagulate, solidifying into the continuous filaments. That's how it works in the wet spinning process. And if you look at the different spinning processes, yeah, if we look at this figure, so there are many spinning processes, like such as simplified process for first, it's a melt spinning process. And you look at this, it's a melt spinning process in which the polymer is melted through the extruder and directly drawing into the fibers. For example, polyester and nylon, which can be, formed by the fibers of these polymers can be formed by melt spinning. The another one is dry spinning, in which the pressures, the solution of polymer is converted into the fiber, and hot dryer are continuously drying this. So it's just known as drying, in which the polymer is dissolved in a volatile solvent first and extruded into warm air. The solvent evaporates, leaving solid fibers only, such as acetate and spandex. These kind of polymers formed by dry spinning. Third is wet spinning. We just read about the wet spinning, in which the solution of polymer in coagulation bath having an anti-solvent is drawn to the spinneret, a tiny plate with holes, and which convert into the fibers, and then you can take the fibers with the precipitation of polymers itself here. Apart from this, if you look at the D is a kind of a gel spinning technique in which, so this is a different type of this when solution is put at the coagulation solvents and fiber take up that the coagulation solvents different and hot oil. It is passed through the hot oil. And if you look at the E, it's the electrospinning, in which electric field is used to draw fibers from a polymer solution or melts, not a coagulation bath. So applying electrical fields, so where we can draw polymers into the fibers. And the last one is centrifugal spinning. They are not that common one, but the melt, the dry, electrospinning, very common spinning process to draw polymers into the fibers. So I hope all this processes of fiber spinning is clear to everyone. If anybody has any problem, I can repeat any of these process again. Okay, so if not, let's move forward with the question. So which fiber spinning method is best suited for thermoplastic polymers? Asking about which fiber spinning method is best suited for thermoplastic polymers. Dry spinning, wet spinning, melt spinning, or solution spinning. Okay, so I just got one answer which says smell spanning. So let us see which is, yeah, it's melt spanning. And melt spanning is the most suitable method for thermoplastic polymers, which soften and melt it when heated. In this process, first polymer is melted, the polymer then extruded through a spinnerate, and the fibers cooled and solidified in air. No solvent used, making it economical and environmental friendly method, and commonly used for polyester, nylon, and polypropylene. So this is the melt spinning because thermoplastic polymers can melted and reshaped on heating. So that's why using this property, these kind of polymers, fibers can be formed by melt spinning technique. Do not use the wet spinning or dry spinning in which polymer need to be dissolved in any solvent first. Okay, I hope this is clear. So moving forward to the next questions. Which of these following polymers is a liquid crystal polymer fiber used in high performance applications? Kevlar, polypropylene, Solene, or Vectran. So which of these polymer is a liquid crystal polymer fiber used in high performance application? Yeah, you got the answer, which is a Kevlar. Okay, so let's look at the answer. So it's not Kevlar, rather it's Vectran. Vectran is a liquid crystal polymer because Kevlar is not a liquid crystal polymer. Vectran is a liquid crystal polymer made from aromatic polyesters, and in LCPs, the polymer chains have a high degree of molecular orientation and rigid rod-like structure, which give exceptional strength and thermal stability to these polymers. If you look at the Kevlar, Kevlar is an aramid fiber, of course, extremely strong and heat resistant, but it is not an LCP. It is not a liquid crystal polymer, and it can be used in wood toothpaste and composites. Solene, on an other hand, ionomer resin consists of ethylene and methacrylic acid, commonly used in golf ball covers and not a high performance fiber. Polypropylene is a general purpose commodity polymer, lightweight, cheap, but lacks high performance and LCP properties. So for the liquid crystal polymers, Vectran is a liquid crystal polymers. Kevlar is a high performance polymer. No, but this is not a liquid crystal polymer. It's a normal polymer consists of aramid fibers. I hope this question is clear. Okay, then moving to the next question. The elongation at break of fibers is primarily controlled by. So because elongation at break of fibers is a very important property of during the fiber spinning, it decides the properties of different fibers. So how it's primarily it can be controlled by either fiber color, solvent evaporation, drawing and heat setting, or density of the spinneret. So, among which of the following options elongation at break of fibers is primarily controlled? Density of spinneret, option D. Let's see whether it is correct or not. Correct answer is not density, it's C, drawing and heat setting. And if you look at elongation at break, is the percentage increase in fiber length before it breaks under tension, at the final point, whether till whether you can draw a fiber, and it tells us how stretchable or ductile fiber is. And if you look at the drawing, when fiber are stretched after spinning, the polymer chain became more oriented and aligned along the fiber axis. This reduced elongation, became stiffer, less stretchable, and increased the tensile strength. Another one is heat setting. So it's a heat treatment which locks the molecular orientation and crystallinity. It stabilizes the fiber dimension and further control elongation. Thus, drawing and heat setting directly tune the elongation at break. So it's like because how much we are drawing the fiber, and if we are doing the heat setting at that point, that decide what is the elongation of break, and that can be controlled by this drawing. If we draw the fiber in very much length, that means that it is become very stiff, elongation at break. became very, very low at that point. If fiber is not stretched that much, that means it has a stretchability remain itself in it, and it can be stretched further. So drawing and heat setting, these are two properties which can control the elongation at break of fibers. It's not the density of spinnerate, not the fiber color, and the solvent evaporation. These property cannot control the elongation of break. Rather, it can control, the fiber strength or the fiber quality, kind of those things, but cannot, the elongation at break. Okay, so moving forward to the next question then. Which characteristics of polyolefins contributes most of their chemical resistance? I guess we are just left with some last questions of this session because most of the application and the things we already covered in this and the last session. So there are some last remaining questions. So which characteristics of polyolefins contributes most of to their chemical resistance? Because of their non-polar molecular structure, the presence of hydroxyl groups, high crystallinity, and ionic bonding. Yeah, I just got a single answer which says A, non-polar molecular structure, which is make to their chemical resistance. Okay. Let's look at the answer then. Yeah, it's A. It says non-polar molecular structures, polyolefins such as polyethylenes and polypropylenes. They are made up of long chain of carbon and hydrogen, like CH2, CH2, things like this. In polyethylene and in polypropylene, there is a structure of here CH3. So the most of them considered of non-polar molecular structures means they lack strongly charged or reactive groups like hydroxyl, carboxylic, or amine groups. And because of this non-polar molecular structures, they do not interact easily with polar solvents because like such as waters, alcohols, and acids. And that's why they can be, chemically inert and just with breakdown or swelling in most organic solvents. They are hydrophobic nature, make them suitable for chemical containers, films, and pulps. They can be used in such application areas. So this is the only option. The non-polar molecular structure make them uh, very good for the chemical resistance. If you look at the other options like presence of hydroxyl group, no, they do not consist of any hydroxyl like OH groups. They have high crystallinity. Yes, that's true. But that do not contribute to their chemical resistance, and the ionic bonding. They don't have ionic bonding. They have chemical bonding in to them. So it's the only reason like non-polar molecular structure which contribute to their chemical resistance stuff. And chemicals like the solvent like water alcohols are resistant because they cannot dissolve in such salt polar solvents, and because of their inert nature, they cannot be uh, swell into the organic solvents, and that's why they can be used in different applications like chemical containers, films, pipes, and to form things like that. Okay, so which bonds are typically polar and that are most commonly found in a polymeric material? Yeah, that's a good question actually. If you look at the polar means the groups like OH. This is written here like the OH, carboxylic, and amine. So if you look at the nylon, the nylon has many OH, NH kind of structures into that because it is formed from adipic acids and hexadyl methylamine. So they are groups like COOH. So this is a polar groups consist of, and that's why it can easily dissolve, and it can easily attacked by polar solvents like water, because water, the formula of water is H2O. The formula of ethanol or alcohol, something like this, is CH3, CH2OH. So they consist of these groups, OH, SHCOOH. So because of this OH and H groups, they are polars. So, and if you look at these, they do not have any group like O, N, C double bond O kind of. So they are not considered as polar. So nylon, polyurethane, if you look at the structure of polyurethane, you will find also consist of groups like these, so they are also polar in the nature. So if any polymers has groups like these OH, NH, COOH kind of those, which consist of acids, alcohols, and stuff like this, they are polar in nature. But polypropylenes and ethylenes and stuff like these polyolefins, they do not consist of such structure, and they just form from the CH2 group. So they only have two, the compositions like carbon and hydrogen only. And that's why they considered as non-polar structure. And if you want to dissolve these kind of polyethylene or something, you need to be non-polar, to take a non-polar solvent. Because, there is a phenomena, I don't know, you must have heard, like dissolves like, which says like dissolves like, which says, polar molecules can be dissolved or can be swelled. I'm not saying exactly dissolved, but can be swelled in polar solvents. And non-polar groups or non-polar polymers can be dissolved or can be swelled in non-polar solvents. And non-polar solvents, as in, you can go for like toluene and the solvents like which do not have these kind of groups in that also. So yeah, they can be, swell and dissolved in that, but not in the mediums like water, alcohol, or acids. That's why the moisture, in that atmosphere, moisture, water, these are the moieties present in the environment, and that's why they cannot directly harm these polyolefins, and that's how uh, they are chemical resist, and that's how they can be used in different application areas like chemical containers, films, and pipes, and it's mostly single-use plastics. All the stuff like made from these polyolefins generally. So I hope this is clear. Okay, moving forward to the next. Yeah. So which of the following best describe tenacity in textile fiber? So, which of the following best describe the tenacity, the ability to fiber to absorb moisture, the resistance of a fiber to heat, the breaking force per unit of linear density, and the fiber resistance to filing? Okay, so I got an answer, which is it's C, the breaking force per unit of linear density. Let us see. Yeah, it's C. Tenacity is a measure of how strong a fiber is specifically referred to the force required to break the fiber, normalized by its linear density, and this allow comparison between fibers of different thickness or sizes, typically expressed in gram per denier or centene net newtons per text. And this property is very important in evaluating how well a fiber will perform under stress. For example, ropes, seat belts, or performance textiles. So that's how the tenacity measure the force required to break it, which is the force per unit, breaking force per unit of linear density. Okay, so the next question is which of the following fiber is known for having high elongation at break? If you look at it, which of the following fiber is known for having high elongation at break? Kevlar, nylon, cotton, or glass fiber? Hmm. Okay, so which of the following fiber is known for having high elongation at break? And the correct answer is B, nylon. Yes, it's true. If you look at different polymers, so Kevlar is an aramid fiber known for very high strength and low elongation. It is stiff, and that's why it is used in bulletproof vest, composite, and protective gear. Elongation in break is lower than, less than 2.5 to 4%. But nylon, on another hand, is a synthetic fiber with excellent extensibility. And that's why it is because of its stretchable and flexible behavior and high elongation of break. It is used in hosiery, parachute, sportswear, and industrial applications like this because it's typically 15 to 30% or more. Cotton, on the other hand, is a natural cellulose fiber. Its moderate elongation at break, 6 to 10%, but not as high as nylon. Cotton is strong, breathable, but not high elastic. Glass fiber is very stiff and brittle. It has very low elongation at break, even less than Kevlar, and that's why it is used for structural strength, not for the flexibility. If you need to provide a strength to something, you can add glass fibers into them, but it is not for the flexibility. So the only polymer which have a high elongation and break is nylon, and that's why it's used to make ropes and parachutes and stuff like sportswear and everything because it requires the stretchability. So I hope this is clear. The question is clear to everyone. So yeah. Now, the next question is identify the incorrect statement related to commonly used polymers in sports equipment. So, which of the following statement is not correct related to polymers in sports equipment? Now we have studied and read many polymers like these, so we can easily find out the incorrect statement among these. So I got an answer which says that C, polyethylene commonly used in body armors because it is flexible and tough. So let's see what the answer is. No, it's not C, it's D, which is polystyrene is used in high performance sports composites due to its elasticity. Polystyrene actually is a brittle, rigid thermoplastic commonly used in packaging and to form cups and containers and insulation. It lacks elasticity, which makes it suitable for high performance sports composites that require mainly with the flexibility, toughness, or impact resistance. High performance, the polymers consist of a carbon fiber, glass fiber, Kevlar, polyurethane, epoxy resin, such stuff like this. Polyurethane is not exactly elastic, and that's why it cannot be used in high performance sports composites. On the other hand, if you look at the other options, like Kevlar is used in protective gears like gloves or helmets, that's true because it is a high performance polymer with the high impression and impact resistance. Vectron is a liquid crystal polymer we just read, known for its low moisture absorption and high strength. Polyethylene is commonly used in body armor. It can be because it is flexible and tough. Yeah, that's true. Because polyethylene is a flexible polymer and also a tough polymer, so it can be used in body armor and it should be used. Polystyrene, on other hand, cannot use in high performance sports because it is not elastic. It is a brittle, and that's why you have seen the cups and form and the thermocols and everything's like this. It is formed from polystyrene, and it is very brittle. You can just break it like this. Okay, so I think this question is clear to everyone. Moving forward. Okay, that's all for the day. And I hope all these questions are clear and all the concepts we have read till now are clear to everyone because this was the last session of this course, Polymer and Process Engineering. I hope you guys enjoyed this course and you got the concepts and you got the questions right. And this sessions, I hope they helped you to solve these assignments of related. And I hope this assignment, 12 assignment can also be solved with the help of this session. So I wish you all the best for, the future one. And yeah, thank you so much all for your help and time. Thank you so much to you too for your time into the sessions. And I wish you all the best for the future. And let's end today's meeting. Thank you so much all.